Hello there. In this video, we're going to tackle optimization. Namely, we're going to look at gradient descent and how, just show a simple example in Excel of how gradient descent works. So without further ado, let's go ahead and switch over to the Excel example. Again, I am going to drop these into a Google Drive and outline in the description where you can go and get this specific example if you want to look at the formulas and play with the Excel spreadsheet yourself. So let's start off and let's describe what's going on here. So what we have here is we have single linear regression. So I'm going to highlight some columns. This is our one input X column. We have one output column Y. And then I went ahead and normalized the values of the X. So that's what you have here is this column. I've actually named everything. So you see up above, we have X for this. This is named Y, so you can see that in the upper corner. I have this prediction column, which is Y hat, loss column, which is L. So I've named everything appropriately. And as you can see up here, we have this direct solve. So this is using linear algebra to directly solve for the model parameters. But if you don't know that and just start with 0, recall that we can go up and use what is a solver tool, within the data tab, and it will bring up this box. And so for these solver parameters, again, we can select that cost function. This is the average of these loss values. And we want that to be set to iteratively go to a minimum, and do that by changing which cells? Well, change these zeros. Okay, and leave everything else the same. Let's solve for this. Again, I'll drag this over so you can see within this window. Keep solver solution or restore original values. Let's keep them. And now as we kind of look over here, our direct solve and our model parameters are the same. So this iterative optimization technique, which uses gradient descent, was good at actually obtaining the same model parameters that a direct solve will do. So that's really great. But how does it work? So now we're going to kind of step through what's actually going on. So, before we do that, let's go ahead. This prediction, again, is a matrix multiplication of x times theta. Let's set it back to these zeros. So this is going to be our initialization. Now I'm going to hide this, and we're going to first look at one step in gradient descent. So I'm going to discuss a little bit of the math here, but hopefully you can kind of see too how these matrices set up really nicely so that you can do these iterations very quickly. So what you have is each of these rows corresponds to the x, y pair. So you're going to have a row of these derivatives for each one of these. And then if you look at a gradient descent step, what do you have? Well, you have the initial model parameters. Again, I'll try to outline down below. Down here by this equation. You have the initial model parameters, and you're going to subtract alpha times this derivative of the cost function with respect to the model parameters. Now, you don't do this directly. You can separate all the different functions involved with gradient descent or with the prediction, and sort of build up what is this derivative. So the first thing you have to do is take the derivative of the loss with respect to y hat. Well, what was the loss function? if you kind of look up here, you know, I'm highlighting this equation. The loss is equal to y minus y hat squared. So what's the derivative of that with respect to y hat? Well, you want to take the exponent 2, move it out front. So it's 2 times y minus y hat. Then you reduce the exponent by 1, so that just makes it 1. Then you want to take the derivative of what's inside. So the derivative of what's inside with respect to y hat is negative 1. So you end up with this equation here, 2 times y minus y hat times negative 1. So you can go ahead, we can look at this formula. This formula actually traces back to y and y hat are dynamic arrays. You know, so there's that part of the derivative. The next part of the derivative is the derivative of y hat with respect to theta naught and with respect to theta 1. So if you look kind of down below, hopefully you can see this on your screen. Yeah, there's the equation, this theta naught plus theta 1 times x. If you take the derivative of theta naught with respect to theta naught, that's 1. And it's 0 for this, since there's no theta naught there. You know, so you get a column of 1s, like I'm showing up here. If you take the derivative of this term, again, with respect to theta 1, well, theta naught with respect to theta 1 is 0. Theta 1 times x with respect to theta 1 is just x. So what you end up with for this new dynamic array after taking these derivatives is just equal to x. You know, so that was fairly easy also. So now you have the derivative of the loss, and you have the derivative of y hat with respect to these model parameters. If you multiply those together, now for each one of these rows, you're going to get the derivative of the loss function with respect to the model parameters theta. And then, you know, from there, what we want to do is we want to average each one of these columns to get the derivative of the cost function with respect to theta. So if you look at the equation down below, again, it's the derivative of the cost function, not the derivative of the loss function. So you're going to average each of these columns. I've done that up above. You know, using this function, I had to actually you know, use this bi-column function in order to create the dynamic array. You know, what it actually is doing is I selected everything down below in this blue box. I use this lambda function, you know, and I identified C as, you know, to reference each column. So each column it's going to take an average and return a value within this new array. So now we have the derivative of the cost with respect to theta naught and with respect to theta 1. And so the last part here is you are starting with an initial theta values of 0 and 0. You know, and our new theta values, okay, so what's going on here? Well, our new theta values are these theta initial, so 0 and 0. You're subtracting N3 is our alpha, so minus alpha, and then multiplied by this N4 and O4. These are our derivative of the cost with respect to these theta parameters. And so what you actually get, you know, you see it went from 0 and 0 to 126 and 23, and the cost function has went down accordingly. So if you want to see the formula for the cost function, again, I'm going to actually separate these out so it's easier to see. Okay, so the first thing we do here is we identify our theta parameters. So we identified the 0, 0. Our x is equal to the x array. The y is equal to the y array. We did y hat. That's a matrix multiplication of x times theta. Again, we had to transpose theta because it was the wrong matrix dimensions. You know, the loss function is y minus y hat squared. The cost function is the average of the loss. And then we want to return the cost function. So that's what we've done here. And it's the same formula, down below. But you can see that the cost function has went down, in this first iteration by quite a bit. Now we're going to skip over to what this looks like after multiple iterations. So I haven't actually filled in all of the formulas for this, but again, we're going to start with this theta initial of 0 and 0, and you can see our cost function here. So we have, I just did for each iteration, our initial theta values are in this dynamic array. And this is going to be this derivative of the cost function with respect to theta. So we're going to do all of what we did in that first iteration all in one step. And this is where this let parameter is really, really handy. So you can see that we identified the theta parameters off to the left. We have x is equal to x, y is equal to y. So we've just kind of created these new variables, x and y, that operate within this let function. But we've actually assigned the cells within our spreadsheet that are named x and y to these new variables. Y hat is just matrix multiplication of x times the transpose of theta. Our loss function is still y minus y hat squared. Our cost function is the average of the loss function. And then if you remember, the derivative of, it's actually the loss function with respect to theta, was -2 times y minus y hat. Actually, the -2 is combining the 2 and the -1, so just did that all in one step. And then we're going to multiply that by each column of x. So this gives us that entire matrix all in one step. Again, the matrix I'm talking about is this one right here, right? So that's that parameter or variable within that let function gives us that. And let's go back over here. So we were right here. And then the last step is simply to take the average of each of those columns, and that gives us back our derivative of the cost function with respect to theta. So there we go. That's the first iteration. And now what we want to do is we're just going to iterate this. So this is going to be equal to this initial value minus alpha, which I've named alpha here, multiplied by this new dynamic array, which is this derivative function, and enter. So there's our new theta value. I've copied over the formula that computes the cost. You can see that it's going down. Now I can just, actually copy some of these cells down. So you can see how, as you copy it down, the cost function continues to get lower. I can go ahead and drag this all the way down. I've done 100 different iterations here. And we want to go back up and drag this formula down as well. And you can see from this formula that, this is changing as we drag it down because, I didn't include those dollar signs, right? You hit F4 and you can have that stop. Here I wanted it to shift as we drag and copy this function down. So escape, I'm going to click on the corner and I'm going to go ahead and drag that down because we want 100 iterations of this. Okay, you can see by the end, look, these derivatives are 0. We could probably expand this out if we wanted, and it's something really, really, really small. So there we go. Okay. And so now you actually, what I did is theta naught and the cost function. So you can see that as you go along, it's actually converging on a value there, which is a 633, and theta 1 is converging to 122. So these were in line with what we got with the direct solve. So here we've done essentially what the Excel solver function does. Now, how does it know when to stop? Well, this one's really easy. As you can see that the cost function is going down, and even as we scroll down, it eventually stabilizes. So what it actually does for when to stop is there's usually some converge threshold, and all it's going to do is, if you highlight this formula, you're going to take the cost function from the iteration before, you're going to subtract the cost function at the present iteration, and this is going to tell you like how much the cost function improved. And so once it gets below a certain value, say here we just did 1e to the negative fourth, then it's going to stop. So I did a calculation cell up here, and it looks like it converges at step 49. Now, one thing to understand is we do have this 0.1, this alpha. Again, when we talked in the videos, this is referred to as a hyperparameter. It affects how we do the optimization and how we even obtain the model parameters in some case. But upon execution time of our model, you don't really need these hyperparameters. So alpha, what happens if we start to change alpha? Actually, many times, people will set it to a really low value, and this way it's going to, progressively get lower and lower, but you can see here that this, it now no longer converges within 100 steps. So certainly there's some impetus to actually start to increase it, right? Even 0.05, it's a bigger step. You saw how it's taking bigger steps as it goes down this parabola here to obtain the minimum value. 0.1 was where we were at. That actually very smoothly kind of converges to these optimal model parameters. What happens if you keep increasing it? 0.2, let's go 0.4. Yeah, actually some of these bigger step sizes gets there a whole lot quicker. You can see 0.4 converges on step 8. 0.6. Okay, well here you see it's kind of shot to the other side of the parabola. So if you take too large of a step size, you may actually shoot past the minimum and have to, iterate back and forth. 0.8. Yeah, you can see it kind of bouncing off this parabola loss function to try to obtain this minimum. 0.9. Even more, but it is converging, so for all of these different alpha parameters that I've selected so far, it is converging to these optimal model parameters, which is really nice. But there is a problem with selecting it too large. So here we go. Let's select an alpha of 1. Yeah, this is really interesting. So now our slope term seems to have converged. So you can very clearly kind of make out the parabola loss function or cost function with respect to theta 1, and it's jumping back and forth in order to converge. But for theta naught, it actually doesn't seem to be able to converge. It's moving in the right direction, so the cost function is getting lower. Maybe if you let it go enough steps, it would eventually obtain the right theta naught parameter, but it's certainly having problems converging. And if you do much too high, so let's say an alpha of 2, again, this is modifying really the step size. you can actually get an exploding cost function. So here, if you look in this column, the cost function is steadily increasing. So you've actually, you're going in the wrong direction. So that's how these hyperparameters, especially in gradient descent, what this alpha hyperparameter does. And this example is just to kind of show you how gradient descent works on a very simple problem. So with that, thanks for joining. Hopefully this showed a little bit of how gradient descent works, but also as you get into the derivatives and thinking about the chain rule and how that works with neural networks, it's nice to see a simple example like this because some similar things show up within neural networks. Obviously, there's a linear regression part to the node. And the fact that the derivative of that with respect to the model parameter is equal to x makes it really easy to start to think through what these matrices, these derivative matrices look like within the chain rule within a neural network. So with that, thank you for joining, and may the course be with you.